Everyone, and welcome to a live stream for Chemistry 222. This is brought to you by Portland State University and the Learning Center at Portland State. I want to start off by, I'm going to post a few useful links in the chat window. First, I've got a link to the Learning Center so you can check them out and see all the different useful resources we have for students at the Learning Center here. We can also give you a link to their Facebook and Instagram page. Pasting there in the chat. I'll explain a little bit of how all of this works. Every Friday at noon, I'm going to be tuning in and kind of giving a rough overview of what I believe you guys have covered this week, and we're going to cover a few questions from the book as well, trying to hit a few for every different topics. This is supposed to be kind of an interactive thing, so if you log on, watch us live, you can chat via the chat window that's there, and you can ask me questions to explain things further. If you have specific problems you want to go over as well, I'm happy to do that. It's supposed to be kind of a group interactive situation here. So I'm going to get started doing a quick review of the material that you guys have covered, talking about acid and bases, conjugate pairs, the strengths of acid and bases, and how to calculate pH and Ka values as well. So let's get started. First, we're going to talk about the idea of an acid and base, specifically the Bronsted-Lowry acid base. And what this basically is it's the idea that a compound can donate a proton or accept a proton. A proton is essentially an ionized hydrogen. So an acid, we can say, is a compound. I'm going to switch over to there we are. A compound that donates a proton. So what would you think that a base is? Feel free to chime in on the chat if you have any questions, comments, concerns. So if an acid is a compound that would donate a proton, what would that make a base? Base would be a compound that would accept a proton. So an acid is something that would lose a proton, lose a hydrogen. A base is going to accept that hydrogen or want to take that proton in. And this makes compounds have what we call conjugate pairs. And conjugate pairs are basically once the acid or base has accepted or lost a proton, it's that change in the compound. So we can say that a conjugate base is the species that's left over after an acid donates a proton. Which means the acid loses a proton to another base, and that base becomes more acidic. The leftover species is now lacking a proton, which makes it the conjugate base of the acid. Examples of this is the basic example. If we take like HCl, I mean, Cl is not really a really strong base. It's actually an incredibly weak base. The stronger the acid, the weaker the base is going to be. But that's going to produce basically H+, something along those lines. where HCl is going to be the acid, and we're going to add that in with H2O, we'll say, a liquid form. And that's going to produce kind of this dissociation between those. So then the conjugate acid is the species left over, or the species that's created after the base accepts a proton. So if once the base accepts that proton, it becomes the conjugate acid. It's basically the base that turned into an acid, where the conjugate base is the acid that turned into a base. And we can see that we have a picture from your textbook down there. So on this chemical formula down here, we have water, liquid water, and ammonia. And ammonia is acting as the base in that case. It's got a pair of alone pairs there, so it wants to kind of take a proton in. Here, water is acting as an acid, so it's got a couple extra hydrogens. It's going to lose one of its hydrogens there. And we can see that in the products. The water has lost a hydrogen there. It's now negatively charged, and this is now the conjugate base of this water here. The ammonium here, which is NH4 plus, is the conjugate acid of ammonia because it's now gained that hydrogen. It's got the positive charge there, and it's the conjugate acid of ammonia. One of the water in itself, you can say H2O as a liquid, and we can really just kind of add it to itself in this case. So there's just a lot of water in there. There's nothing else really being added. Water is in equilibrium with hydronium, which is H3O plus, and hydroxide, which is OH minus. So water is constantly changing into hydronium, losing a proton, gaining a proton back. So it's constantly exchanging protons with hydronium ions and hydroxide ions. And this is kind of this constant equilibrium state, basically. And at different temperatures, basically, there's different concentrations of these all. But we say at room temperature, the basic concentration of these is going to be equal to its Ka, or Kw, we call it. So Kw, just like we learned with the equilibrium constants before, is going to be equal to the concentration of the products divided by the concentration of the reactants. And in this case, what are the products? What do you think the products might be for this reaction? Any guesses in the chat? H3O plus? Yeah, that's good. That's one of the products. That's hydronium. And OH minus. Perfect. Those are the two products for this reaction. They're just over here on the left-hand side. How about the reactants? What would we put on the bottom down here for the reactants? Anything? Perfect. That's what I was looking for. It was a trick question. Yeah, since these are liquid here and here, we don't count those as part of the reactants there. So this is just going to be our, this is going to define our concentration, or the constant of equilibrium for water. Which for a, and this is always going to be basically 10 to the negative 14. Yeah, so we don't count liquids or solids in the equilibrium constant. So anytime you have something precipitate out, we don't count that as part of the product or the reactant in that case. Same thing with liquids as well. But anything aqueous is just ions floating around in there. That's when we start talking about the concentrations of them. So this relationship for the K of water is a really important one because it has to do with the equilibrium constant of water at room temperature. So this is usually at 25 degrees C. And if we increase the temperature drastically, this is going to go up. If we decrease the temperature, it's going to go down, so on and so forth. But normally we're looking at the K of water, KW, is almost always going to be listed as 10 to the negative 14. And that's an important thing to do. And we're going to use that to kind of go back and forth between the different K values or equilibrium constants for acids and bases later on. So let's try some of these things on a few problems here. So I'm just pulling problems from your textbook. Kind of jump around, pick some ones that I like every fourth or so. If you have any specific problems you ever wanted to cover or you get stuck on something, you can always bring those there and we'll try to cover those during the live stream. Also, you can schedule tutoring hours with one of our great tutors with a link above if you're watching in the Pingy site to schedule a tutor, and we'd be happy to help you out with things as well. So we'll start with number 6 from your textbook. It says, show by suitable net ionic equations that each of the following species can act as a Bronsted-Lowry base. So let's start with A up here. How would we write a net ionic equation for that one? Any guesses? So if it's acting as a base, it's going to start out just as it is, right? Like this. And once it adds that hydrogen to it, it's actually going to lose that negative charge. But H2S, or HS, is going to be as a product in this case. Or H2S, yeah. There we are. Because once it acts as a base, it's going to gain that hydrogen. So you're absolutely right there. But it does lose that negative charge because that hydrogen comes in with a positive charge to it and balances the charge of the product. But what is it reacting with? It needs to react. So we were saying that this HS minus is going to react with H2O to produce H2S. But what would the other product be for this one? Is the connection still bad? Am I skipping or fluttering right now? Better? Okay. Sorry about that. Oh no. Sorry about it. It's logging you off. Yeah, I think I lost my connection for a second and then it reconnected. Let's hope that doesn't happen continuously. So the other product that's formed here is going to be OH minus. Because for this base, we have its conjugate acid. What would the conjugate acid be for that base? The conjugate acid would be this guy. So in this case, the base here gained a hydrogen, acted as a base, and became this conjugate acid. So it's kind of what that base became once it absorbed that hydrogen is now its conjugate acid. So the conjugate base is now hydroxide as well. And this is the conjugate base for water. Because water was acting as an acid in that case, giving up a hydrogen to your HS minus, and then it became OH minus. Therefore, it became this conjugate base on the right-hand side. But the net ionic equation is really just this guy. Just writing out that equation is kind of the important part there. Let's try another one here. Let's do NH2 minus, acting as a base. So we know NH2 minus has to start out over here. And it's going to be aqueous. What's the other reactant that we're going to have? H2O. Perfect. And then what would the products be? What would the conjugate acid of this base be? Perfect. That's ammonium, and it's neutral now because it gained that positive charge, getting rid of this one negative charge that it had, making it more neutral. And then what would the conjugate acid be? I'm sorry, the conjugate base be of this, because this was a base. This was the acid. OH minus again. Exactly. Basically, you're always going to have OH minus when water is acting as an acid. Let's jump down to number 10. We want to identify and label the Bronsted-Lowry acid and conjugate bases. And we want to do the conjugate acid in each of the following equations. So find the conjugate base and the conjugate acid, as well as the acid and base. So I'm going to circle the acids in blue and the bases in red, or say something to that effect. For part A, we can see that this is going to be my base in this case. Anytime it's negatively charged as a reactant, it's most likely going to be your base. And then that makes, let's go here, that makes this one your conjugate acid. Because in this case, once it gained that hydrogen, it became the conjugate acid of that base. Similarly, water is acting as an acid here, so OH minus is the base. What about part C? Let's jump. We just did that one up top, actually. Let's look at part E. What would the conjugate acid be, or what would the acid be in this one, starting out? HCl. Perfect. And HCl is one of our strong acids, so it always kind of completely dissociates everything. So then that would make this one the base then, right? What would the conjugate acid be? So that would be the conjugate base, Cl minus. It's easy to get those confused. Yeah, exactly. H3PO4 is our conjugate acid. So these two are connected to each other. Well, Cl minus, that's going to be the conjugate base to HCl. These two are going to be connected together. I know it's kind of a little backwards in your head sometimes where you're looking at, yeah, they switch. Because this one went from a base to an acid, so we call it the conjugate acid, but it's referring to the base and the reactants. And the conjugates are always going to be in your products, and your the regular ones are kind of always in the reactants. But you could flip that around, and since it's in equilibrium, it can kind of go both ways. All right, let's try G, this last one down here at the bottom. What would the conjugate acid be? Or sorry, what would the acid be? I should always start with acid and base. Would H minus be an acid or a base? Base, perfect. And then what would the conjugate acid be of that? H2, perfect. So that makes H3OH, which is methanol, be our acid in this case. And this makes this guy here, oops, I should circle that in red, be our conjugate base. And H2, what's unique about H2? Because in this situation, it's not really going to be in equilibrium for a good reason. Anybody have an idea of what that would be? The main reason is H2 is one of your diatomic molecules. And it's a gas. Which means if you were to mix these together and you start producing H2 in your liquid, it's going to start bubbling out. And as it bubbles out, basically, you're removing your product from the reaction. So Le Chatelier's principle is going to say we're going to push that whole reaction to the product side. So it's going to drive this reaction to completion, and you're never really going to get into a state of equilibrium because you're removing this gas from the reaction as you go along. All right, last one. This is this concept of amphiprotic. Amphiprotic just means that the compound can act as both an acid and a base. You're going to see this a lot if you have, anytime you have a hydrogen in the compound, especially if it's not attached to a carbon. Hydrogen and carbons don't break off really easily. But they can act as an acid if they have a hydrogen, essentially. Anytime they have a negative charge or they have a lone pair, they can also act as a base. Negative charge usually means they have a lone pair in there somewhere anyways. So anytime that's true, we can have something act as an acid and a base, and that's what they call it here as amphiprotic. It's like an amphibian. They can go in water or land, and amphiprotic means they can gain a proton or lose a proton. So we want to look at these compounds here and try to identify which ones are amphiprotic. So looking at all of them, A, B, C, D, or E, shout out if you see any of them that you think are amphiprotic. And just put in the letter for it. C. Can C lose a hydrogen? Because remember, to be amphiprotic, we have to be an acid and a base, basically. So if it doesn't have a hydrogen in it, it's not going to be an acid, essentially. So right there, I can cross out these two here, C and D. A, B, and E. Yeah, A, B, and E are good. Because A is water. We already know they can act as an acid and a base. This oxygen has two sets of lone pairs on it as well. B, it's got hydrogens in there, and it's got a negative charge, plus all of these oxygens are going to have some lone pairs on them, most likely. So this one, both of these are good. And then this last one down here, we have a hydrogen, and we have a negative charge. This one, it probably won't act as a base really easily, but I mean, it still will. It's still possible to do so. So you can see that a lot. There's a lot of them, especially stuff like this one here. This one actually, it can be H3PO4, right? So that could lose 3 hydrogens. It could be acidic. It's very acidic when it's like this. And then when it's like this, it's mildly acidic. And when it's like HPO4 minus 2, it's not very acidic at all at that point. So it has different stages of acidity, and the strength of acid is weaker and weaker as it loses more and more protons. So let's go on to the next topic. We're going to talk about pH. How do you all feel about pH and the idea of pH, pOH, and calculating the different pH values based on concentrations? So that's good. We're going to go over it a little bit. So it's this concept, we're using logarithms now, and that's what kind of makes it confusing, right? Because like, what is a logarithm really? And this equation you see at the top of my screen here, let me zoom in a bit so it's bigger. It's the P of X, where X is going to be equal to basically the concentration of some species. We usually refer to this as pH because we're looking at the concentration of hydrogen ions, which are usually positive. So if we know the concentration of hydrogen, you might also see this written as hydronium. They're really the same idea. Any hydronium ion can become a hydrogen ion, just dissociate with the water, and then can be floating around in there. So those two are used kind of interchangeably. But if we're looking for the pH, really we're just using this function, the negative log of the concentration. So if I had a concentration of H plus that was equal to, say, 5 times 10 to the negative 3, we could calculate the pH by just plugging into our calculator negative log of 5 times 10 to the negative 3. So I've got my calculator here. This is kind of like a TI 83, 84 style. I'm going to put in the negative symbol, this log here on the left-hand side, and put 5. I can even use this little EE. So I put second EE, or you can just type in times 10 to the power of, and then do negative 3. I'm going to have a pH there of 2.3. So that's kind of the simple way to calculate things. If you know the pH of something, so if we were to say we have a pH is equal to say 5, say 5.2, just making up numbers here. We can calculate that in a similar way, kind of in the reverse. So to do this in the reverse, really we do what we call the anti-log, which is really, this is log base 10. You might see 10 in there sometimes. So if we take 10 to the power, that's annoying. That doesn't usually happen. So I was saying, and I might have to have people log in again, so I apologize for the lack of connection. I'm going to get that fixed in the future. So if I take this log to this power, this is just equal to the concentration of H plus. I need to do it to both sides of my equation. So that means I'm also going to take 10 to the power of negative 5.2. So we move to this negative over to the other side. So if I say this is equal to log concentration of H plus, I'm moving this negative over to the other side, and I'm taking both sides and making them the exponent under the base of 10. So this is a way to calculate what your concentration is if you know the pH, just by plugging this guy into our calculator. So doing that, 10 to the power of, I should use a parenthesis, negative 5.2 tells me I have a concentration of hydronium of 6.3 times 10 to the negative 6. So it's a way we can calculate that pH and the and go back and forth between concentration and pH values. We can also do that with hydroxide instead. So taking the concentration of OH, if I say negative log of that, this is all going to equal what we call POH. And that's the same idea. We can get that POH equal to the negative log of the concentration of hydroxide minus. Any questions on calculating pH based on the concentrations that we have of hydroxide or OH? Cool. So we can expand upon that and say that if we take the P of Kw that we talked about earlier, right, that's going to equal the negative log of Kw, which we know is equal to the negative log of the concentration of H plus times the concentration of OH minus. So that's what we define Kw as, way back here somewhere. There we are. Concentration of hydronium times the concentration of hydroxide. And we say that that's equal to, at room temperature, negative log of 10 to the negative 14, which is just going to equal 14. So we can actually break this up using laws of logarithms I won't go into just the log of H plus minus the log of OH minus. And this we can see is basically pH plus OH, which is equal to 14. So the sum of your pH and your OH, or POH, I'm sorry, is always going to equal 14. So if you know what your pH is, you can then subtract that from 14 to get your OH. And there is a fun little box. Of course. I enjoy doing this. It's a lot of fun. There's a fun little box here. You can see on the top above me, we have hydronium in the top left corner, and we can actually convert to the concentration of hydroxide by taking the Kw, which is 10 to the negative 14, and dividing by the concentration of hydronium. And that'll get us this guy over here. So I'm going to flip to this page real quick, and I'll write these out. So I can say that the concentration of OH is equal to Kw divided by concentration of H3O+. That's just moving from the left to the right of that box there. I can move backwards in the same way, saying that the concentration of H3O+ is going to be equal to Kw divided by OH minus. So it's a way to kind of go back and forth between the concentration of hydroxide and the concentration of H3O+. Similarly, we can go from the concentration of H3O+ down to pH, the bottom of my screen. You're welcome. I'll see you next week. I just want to say one thing before you leave. Also, these are going to be recorded and posted on YouTube, so definitely check out. You can watch the whole thing if you can't tune in live. But if you can tune in live, you can also ask questions and stuff to make sure you understand things. I'll see you next week. So to find the pH, we just have to use the negative log of the concentration of H3O+. Right? So that's kind of moving from the top corner down to the bottom corner of that box. And we can go backwards, because if we can take 10 to the power of negative pH, and that's going to equal the concentration of H3O+. So that's going kind of up and down on the left side of that box. If we want to go from pH to pOH, well, I can say that pOH is going to equal 14 minus pH. Similarly, pH is going to equal 14 minus pOH. So that's kind of moving back and forth on the bottom of that box. And to go up the right-hand side, we can connect pOH with pH, very similar to what we did on pH, where pOH is going to equal the negative log of the concentration of OH minus, and the concentration of OH minus is going to equal 10 to the power of negative pOH. So just kind of working my way around that box. This box here, I think your teacher should probably have that somewhere in their lecture as well. I stole it from one of the teachers myself. It's a really useful thing to do. There's similar types of relationships when we get into Ka as well, because Ka is just the equilibrium constant of acids, and we can talk about how to convert from concentration of the acid to the Ka value to the pKa value and so on in a very similar manner. Any questions on kind of jumping around between that box so we can transfer from concentrations of hydroxide and hydronium to pH, pOH, going back and forth between those? All right, if not, I'm going to, one more thing I want to mention about pH and these values we get. Because we see these values on here where it's like, oh, it has a pH of 5, or it has a pH of 7, or pH of 10, or something to that effect. What does that really tell us? So as the pH value increases, the acidity, I think I spelled that right, it actually goes down. So the more acidic compounds are going to have a lower pH value. As the pH decreases, the acidity, oops, I read a B for some reason, increases. Kind of the same idea but backwards. And neutral is when the pH is right in that middle. So I can say even something that's neutral is going to have the concentration of hydrogen equal to the concentration of hydroxide. When those two are equal, the pH is going to equal the pOH. And since we know we can subtract one or the other from 14 to get the other one, that means they're both equal to 7. Assuming it's at room temperature. Similarly, if for acids, for something to be acidic, that's not it. There needs to be a greater concentration of H plus compared to OH minus. This means the pH is going to be lower than 7, which means that pOH is going to be higher than 7. And then that also means, of course, for something to be basic, we would say the concentration of hydronium. I always write H plus, but it's the same thing as H3O plus. It's going to be less than OH minus. So we have more base in there than acid. There's more OH minuses floating around in there. And that means the pH is going to be greater than 7. So that's a way to define whether it's neutral, acidic, or basic. And anything right around 7 is usually neutral because you're not going to get a lot of acid-base reactions there. But some of these relationships up here on how to convert between all of these things are really going to be the key thing that you're going to use, because a lot of times you'll have concentrations, you'll have to turn it into bases and other things like that. So here's a little scale. Let me switch back to this guy, a little bit bigger. And we can see the neutral is in the middle of pure water. And here's just a few examples. I just took this straight out of your textbook, so if you've seen this already, that's great. But I think it's a good thing to recognize kind of like how acidic some things are compared to other things. So rainwater is slightly acidic. Coffee, which I love to drink, is also slightly acidic with a pH of about 5. Wine, which definitely don't consume in large quantities, you're looking at about 3.5. Your stomach acid goes in there. It needs to be fairly acidic to help kind of break everything down. It's just under 3. We get stuff like lime juice, which is a really good preservative, and that's going to be closer to 2, so that's really acidic. And then you have your HCl, your really strong acids. Those are really close to 0, basically. So that's why they're really strong acids. They completely dissociate from everything. You're not going to really have much equilibrium there. Similarly with your bases, your blood is slightly basic. It's floating in there just over 7, 7.5. Baking soda is right in here, so it's at about 8.5. Your ammonia, which don't drink ammonia, it's going to be closer to 12, where bleach is going to be incredibly basic as well. Pure NaOH, that's sitting at about 14 down there. So those are just kind of just the general scale of different things, so you can get an idea of what your household products are acidically and basically. A lot of your hand soaps and stuff like that are fairly basic, so they'd probably be somewhere kind of in this range here. And such like that. So let's try a few problems here. We got about 13 minutes left. So we're going to use some of these to calculate the pH and pOH of each of the following at 25 degrees C, for which the substance is completely ionized. So we have a few different concentrations here on number 18. So looking at A, we have the concentration is 0.2 molar of HCl. So these are going to completely disassociate, which means we can assume that the concentration of hydrogen in this case is equal to the concentration of HCl. And we don't have to account for kind of the floating around hydronium ions in water because they actually have a fairly low concentration compared to this. Remember, the concentration of a hydronium is about 10 to the negative 7. In this case, we're at 0.2 molar, so we're much higher concentration than that is. So if we were to try to account for it, it would just be lost in the sig figs at the end of the day. So we just ignore it, saying that it's very small compared to otherwise. So doing that, if you wanted to calculate the pH and the pOH, the pH would equal negative log times 0.2 molar. We can leave the molar out for now. It's just 0.2 is the molarity of it, which is the concentration of it. So we can plug that into our calculator, hit negative log 0.2, and that gives us a pH of equaling 0.69, 0.7 we'll say. I guess 3 sig figs. I should go 6999. Yeah, perfect. You got it. So what would the pOH be in that case then? Yeah, sig figs I'm saying are based on this original concentration. It had 3 sig figs. So I'm just carrying that sig figs over. Using logarithms might actually have a little less sig figs. I think you might actually go, I forget the exact rule for logarithms, to be honest. So I'm just going to keep it at 3. But usually if you're multiplying, you just use the smaller amount of sig figs. If you're adding a subtraction, make sure you cut it off at the first insignificant digit or first uncertain digit. In this case, with logarithms, I'm just using that same number. You can usually, I see pH at like maybe 1 decimal place, give or take. Since we're so small here, you can go out to 2. It's a good question for your teacher, actually. Either one of those probably might work. But to calculate the pOH, how can we go about doing that? I can switch back to my pH box. You're already on B. You're getting ahead of me. That's great. Let's try it. Yeah, you got this down. That's perfect. But we also want to calculate the pOH according to this. So we can't forget about the pOH there. So how is it that we can find the pOH for both A and B? So if we did that, using the pH, we would end up going back to what the concentration was originally, right? What we need to do, because they have this relationship right above my head, that bottom of that box says that pH, to find pOH from pH, you can take 14 minus pH, right? So we can use that concentration and we can try to convert it to the concentration of the other and whatnot, but that's a lot more difficult. It's much easier to just say 14 minus, say, 0.7, which is 13.3. So that's going to equal your pOH of part A. I also wanted to point out for part B, that value you found, is that for the pH or the pOH? This value here. Exactly, because this is NaOH, sodium hydroxide. So sodium hydroxide completely dissociates. It's one of your strong bases, but it creates a concentration of OH in there, which when you put into the negative log, you get the POH from it. So if the POH is equal to 1.84, then what would the pH be? That sounds about right. Oh no. There it is. There you go. Again, I would keep, we had 3 sig figs, so I'd keep it at about 12.2, give or take. But yeah, that's the right idea. I'll let you do C and D on your own a little bit later if you want. pH does not have units to it. Because it comes out of the logarithm, usually everything that goes into a logarithm doesn't have units, and therefore everything that comes out of it doesn't as well. So it's just a number on a scale, essentially. Kind of makes its own units in that way. Where molarity or concentration, molarity is going to equal moles per liter, right? That should be an L. Great. Let's jump ahead real quick to 22 because I only got about 5 minutes left. We're going to calculate the hydrogen ion concentration and the hydroxide ion concentration in wine from its pH, looking at figure 14.2. So 14.2 is this nice scale here, and we said wine is right up in here. So based on that, I want someone to approximate what its pH is. Can even draw a nice little graph here. Give you a nice straight line across there. Give me an approximation for what you think the pH is. Oh, sorry, the pH is this column here. $3.5? Sure. It's pretty approximate. There's no reason to be super exact here. 3.5, it's somewhere right in the middle between those. So let's use 3.5 to calculate what the hydrogen ion concentration and hydroxide ion concentration is. So that's H plus and OH minus. Using a pH equal to 3.5. So what do we want to do to get that? Let's shoot for this guy first, be the easiest. We're kind of converting from, where's my camera? The left side here, going up by box. From pH to H3O plus. Perfect. Yep, 10 to the negative 3.5. That's going to give us our concentration of H plus. Have you calculated that? What do we get? I'm getting 3.16, say 3.2, 10 to the 4. Perfect, yeah, that's what I got. Takes a while to type all that in. And that would be molarity. So how can we find P, or the concentration of OH based on this? There's different paths we can take. There's no wrong answer here. So we're about running out of time. I'm going to go through it a little bit quicker. So since we started at pH at the bottom of this side and we went up to the top, we can just use the kW to go to the right onto the across the top of that cube there. So if we take the kW, divide by the concentration of H plus, that should give us concentration of OH minus. kW is, of course, 10 to the negative 14. Go away. So that's 10 to the negative 14 divided by 3.2 times 10 to the negative 4. That should give us our answer here. Should be a 1 in there. Divided by 3.2 e to the negative 4. So I'm getting 3.125. So let's go to 3.2. No, 3.1 times 10 to the negative 11, I believe it was. Yeah. Which should equal our concentration of OH minus. And that makes sense. What I look at is I'm comparing these two here, generally speaking, saying that, well, it's more, that's the concentration of hydrogen, this is the concentration of OH. If it's acidic, the concentration of OH should be fairly small because a lot of those OHs have combined into water with these stray hydrogens. We have so many hydrogens floating around, it's more acidic. Also see that the pH is at 3 and this exponent's around 4, right? Good. I like it when someone confirms that I got it right. It always makes me feel better. All right, so that's all I have for us today. Definitely tune in next week as well. Again, videos and recordings of this should be available online through YouTube and the Learning Center. You should also be able to see them below me if you're watching on the Penji site. Feel free to schedule an appointment up top. I usually have tutoring hours on Fridays just after this, so from 1 o'clock till 5 o'clock, I think it is. I think we're all filled up today, but you can book next week out and a week in advance in the future. Thank you very much for tuning in and have a wonderful day.